This is Algebra 2 with trig. We're talking about section 6.4, which is the use of inverse functions. Remembering back, we've learned that the relation is a pairing of input values with output values. Input are your x's, output are your y's. The function, or a function, is a relation where each input value is paired with only one output. So for every x value, you can only get one y value. If that happens, then you have a function. An inverse relation interchanges the input and the output values of the original relation. So you're going to switch the x and the y values. This means that the domain and the range are also interchanged. For example, if your original graph was 0, 6, 1, 4, 2, 2, 3, 0, 4, negative 2, which is this line, and we were to reflect it over this y equals x. Remember, back in geometry we talked about reflecting. You have to be perpendicular to the line. So you take your point that's on your current line, and since we're doing a slope of 1, we're going to do a slope of negative 1, and one diagonal and a half and 1, you land here. This one would land here. This guy would be 1 1/2, 1 1/2, and so forth. So our line is going to be reflected to make this one. They are inverse equations of each other. The graph of the inverse relation is the reflection of the graph of the original relation. The line of reflection is y equals x, like what we've talked about up here. To find the inverse is what we'll be doing today. To find the inverse of a relation given by the equation x and y, switch the roles of x and y and solve for y. In terms of some notes, pretty much saying the same thing. Sometimes your function might be started with f of x equals, so you want to switch that and call it y equals. Then you're going to switch the x and y's. We're going to solve for your new y value, and this is going to give you the new equation. And our notation is f inverse, that's the f negative 1. F inverse of x will give you your new equation. Let's try that. The original graph is not written with f of x, so we're just fine with y. So now we go on to step number 2, which is switch the x and the y, and then we solve for y. So we'll subtract 2, and we'll divide by 4. So we're going to get y equals x divided by 4 minus 2 divided by 4. Or you could call that y equals 1/4 x minus, and this can be reduced down to 1/2. So in terms of our notation, you could call that f inverse of x equals 1/4 x minus 1/2. This and our original are inverse functions of each other. In this example, both the original relation and the inverse relation happen to be functions. We know they're functions because they're both linear, and linear equations are, of course, functions. In these cases, the two functions are called inverse functions. We can test to see if they're inverse functions. To test to see if two equations are inverse functions, we can do f of g of x and get ourselves all the way down to x, and we can do g of f of x and see if we can reduce that all the way down to x. You have to do both. Very important that you do both. Most of our equations will be, if it works for one, it's obviously going to work for the other, but you got to show both. So you notice here when we do f of g of x, that means to take your f function and plug your g, which is our f inverse, into that. So when you plug your 1/4 x minus a half into your f equation, that's 4 times something plus 2. So our something is our 4x minus a half. We're going to distribute our 4 through, so 4 times a fourth is 1x, and 4 times a half is 4 over 2, plus 2 more. So this is x minus 2 plus 2, so we get actually x. So by plugging the g of x into the f of x, I get a value of x. Now I have to try it the other way. Now I have to try g of f of x. So I'm going to take my g function and I'm going to plug my f function into it. To do that, my g function is 1/4 times something minus a half. Well, my something is going to be 4x plus 2. I distribute that through and I get 1x plus 2 over 4 minus 1/2. Well, 2 over 4 can be reduced to 1/2, and those will cross out, and I'm left with x. So in both cases, I've done the x and I've done reduced it down to x for f of g of x and g of f of x. On our next page, we have our last question. We're going to solve a multiple step. Notice that this is a word problem. So when we're dealing with a word problem, we can flip back and look at the small print on this side. In application problems, which is like a word problem, the variables may have specific meanings. For example, P represents profit. In such cases, do not switch the variables to solve for the inverse. We don't switch them in a word problem because the variables are specific meanings. When you were doing it with a normal y equals mx plus b, the x and the y are switched and it just makes a new table. It's no big deal. But when it matters for the meaning of the variables, just rewrite the equation by solving for the original input. Solve for the value without switching. So back on the other side, we're going to read about a small company produces greeting cards. The cost C of producing N greeting cards per month can be modeled by this function. Looks like the cost equals 360, so that's probably $360 plus 60 cents per card that they make. So there's upfront costs for maybe buying the printer, upfront costs. Then there's 60 cents for every card that they make. Maybe that's the paper or the envelopes, the actual ink that goes onto the card. Every card that you make, they're making the point that that costs 60 cents. So here's your equation for the cost. We're going to find the inverse of that. So without switching the variables, we're just going to solve for n. So we're going to subtract the 360. So we get c minus 360. And then we're going to divide by 0.6 or 0.60. It means the same thing. So that's an equation that represents the number of cards. So now we're going to use that equation. Use the inverse function to find the number of greeting cards produced in a month in which the company's total cost to produce the cards was $615. So if we're going to use $615 minus 360 divided by 0.60, that's going to give us the total number of cards. How many cards are going to be made if we spend $615? So that's going to leave us to 255 divided by 0.60, which is 425 cards.